This practice set will focus on problems that do not allow for simplification. So these are problems where the initial concentration is less than 1,000 times different than the K value. So for this first problem, we have this equation where hydrogen gas reacts with iodine gas and forms an equilibrium with hydroiodic acid gas. So in this experiment, we have 1 mole of hydrogen, 1 mole of iodine, and 1 mole of HI, and they're introduced into a 1-liter container. So we are told to calculate the concentration of all species when equilibrium is reached. So initially, we have, and all of these are 1.00 moles in 1.00 liters, so they are 1.00 capital M molar. Now, I'm going to ignore significant digits just to keep everything as clear as possible. So initially, we have 1 molar of everything, 1 mole. And we will change that value, but we don't know how much to change that. We don't know whether we get pluses on this side or if we get minuses on this side. So in order to find that, we need to calculate the Q value. Now, the Q value is analogous to the K value. It's just that the Q value is found at any point in the equilibrium. And it is equal to the concentration of the product raised to the appropriate coefficient times the product of the reactants. And I understand that that's awkward to say, but you multiply the reactants concentrations together like this. So at this particular point in time, which is what Q is measuring, we would then fill in 1.00 for each of these values. So 1 squared is 1 divided by 1 times 1 is just 1. Well, the Q value is 1. The K value was given to us as 100. So the Q value is less than the K value. So we need for this to shift in order to make that value higher. In order to get that value higher, that means our numerator must be higher. So we must shift towards the production of products. So we're going to add to the product side and we're going to subtract from the reactant side. So that at equilibrium, the concentration of my hydrogen gas is 1 minus X. The concentration of my iodine is 1 minus X. And then the concentration of my products then is 1 plus 2X. And remember, we add that 2X because of the 2, the coefficient there in the balanced chemical equation. So now we can put this all into our K expression, which is like the Q expression, except this time we're at equilibrium. And we can set it equal to the K value. So K is equal to 100 is equal to the products squared divided by reactants. Now my products are squared here because of the 2 in the balanced chemical equation. We don't just automatically square the products. There has to be a 2 in that balanced chemical equation. So now this is where, it's kind of simplification. It's how you look at how you view this in order to get the numbers to work. Now you could work everything out the long way, or notice that in the denominator we have 1 minus X times 1 minus X, which is like saying 1 minus X squared. All of this is equal to 100, which is a perfect square. So we can take the square root of both sides. I know I said there was going to be no simplification, but this is a mathematical technique. We aren't eliminating the X values. So we take the square root of both sides and we get 1 plus 2X over 1 minus X is equal to 10. Now we can solve for X. Now again, this practice is really geared towards those who are still struggling with the algebra, so I'm going to take things stepwise. I'm going to multiply both sides by the denominator. So when I do that, this denominator cancels out. So I have 1 plus 2X equals 10 times this. I'm going to distribute that through. So 10 minus 10X. I need to gather all of my x's on both sides. So I'm going, or on one side, not on both sides. So I'm going to add 10x to both sides, which gives me 12x plus 1 equals 10. Subtract this 1 from both sides, get 12x equals 9. So x is equal to, when I divide both sides by 12, 9/12. Well, 9/12 is the same as 3/4, which is 0.75. Now we are calculating in molarity. So this doesn't answer the question, though. The question was, what were the concentrations of all the species once equilibrium is reached? We have this x value, but what does this x value mean? Well, this x value is the change that occurs. So now I need to plug this x value in. So the concentration of my hydrogen is going to be equal to the concentration of my iodine, which is going to be 1 minus x. That x value is 0.75 capital M molar. So at equilibrium, I have 0.25 capital M molar. Now, don't get grumpy about the significant digits. I left the significant digits off of these just to keep everything as clear as possible, just to show you that it was 1. So the concentration of hydrogen and the concentration of iodine at equilibrium are 0.25 molar. The concentration of HI is going to be equal to 1 plus 2x, which is 1 plus 2 times 0.75. So that would be 2.50 capital M molar. This answers the question. So you have to go through all of these calculations to end up there. But what about the quadratic equation? That's the one that everybody kind of groans at. The quadratic equation can be used quickly and efficiently if you have a quadratic solver in your calculator, or if you use the quadratic equation solver that I link in my quizzes. So I will show you the long way and I will show you the linked way. Showing you how my calculator works isn't going to help you much. So we will work with this equation. N2 plus O2 creates an equilibrium to NO. So what is the partial pressure of NO in equilibrium with N2 and O2 that were placed in a flask at initial pressures of 0.8 and 0.2 respectively? We're dealing with a Kp, so we're dealing with pressures. So the Kp of this reaction is equal to a value 0.050, and that is going to be equal to the pressure of NO squared over the pressure of N2 times the pressure of O2. Now initially, let's just write this real quick. Initially, we were told we have a pressure of 0.80 atmospheres for nitrogen and 0.20 atmospheres for oxygen. That's what respectively means. We're going to go first, then second. Now we're going to change some amount. We don't have any NO initially. Because we don't have any NO initially, I know I must be adding to the product side. So I'm taking away from my reactants. So at equilibrium, the pressure of N2 is going to be 0.80 minus X. O2 is going to be 0.20 minus X, where NO is going to be 2X. So now I'm going to put all of this into my Kp expression up here. So this will end up being 2x squared over 0.80 minus x times 0.20 minus x. Now remember that equals a value, and that value is 0.050. So where do we go from here? Well, we're going to multiply both sides by the denominator first. That's going to get rid of the denominator on the left side. And I'm also going to square this 2x. So when I square 2x, I get 4x squared, because remember, I got to square both sides of that. So on the right side of the equation, I have 0.050 times what was in my denominator. But we need to expand this part here. This is using the technique called FOIL. I've seen in some algebra classes they call it other things. I learned it as FOIL. I'm going to present it as FOIL. If you know a different way and it works consistently for you, please keep using it and ignore this part. So I'm going to keep my 4x squared over here. I'm also going to keep my 0.050 over here. I'm not going to distribute that yet. So first, I multiply the first elements of this quadratic here, this 0.80 times 0.2, and I get 0.16. Now I'm going to do the outside. The outside numbers means 0.80, this is outside, times this negative x. So I'm going to subtract 0.80x. Now The I for FOIL is inside. So the inside numbers are negative x and 0.20. That means I'm going to subtract 0.20x. And now the L of FOIL is last. So I'm going to take the last digits. So this part here and this part here. So negative x times negative x is a positive x squared. So that is how we expand that quadratic. Now I can, well, first thing I'm going to do is I'm going to combine my likes. So I'm going to take and add these together. So 0.8x minus 0.2x, this negative 0.8 minus negative 0.2 is just a negative 1. So that is convenient. Now I'm going to distribute this number through. And what that means is I'm going to take this number and I'm going to multiply it by this number. And then I'm going to multiply it by this number. And then I'm going to multiply it by this number. And when I do that, then I've distributed it through. And then I can start to combine everything together. So when I distribute, then I get 0.008 and then minus 0.050x plus 0.050x squared. Now I need to combine everything. I need to put everything on one side so that this equals to 0. That way I can use the quadratic equation. So I'm going to subtract 0.050x squared from both sides, and I end up with 3.95x squared. Then I'm going to add this negative, I'm going to add a 0.050x to both sides. That gets rid of this. And I'm going to subtract this 0.008 so that I have this expression that equals 0. Now, when I put this into the quadratic equation, what I need are these coefficients. This is A, this is B, this is C. Now, this sign value, there it is, this sign stays with the coefficients. So this one is positive and this one is positive. Now, first, I will show you the long way. So the quadratic equation is where x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now we have these values, so we're just going to plug them in. And I put a b. So now we can solve. Now the question often arises, well, how do I know if I'm adding or subtracting? Well, the answer is you're going to do both. So I'm going to try to do this stepwise in order to allow you to check your work as you go. So 0.05 squared is 0.0025 minus, and I'm going to multiply 4 times 3.95 times 0.008. I added instead. Now my number makes more sense. So I'm going to subtract, don't drop this negative, a negative 0.1264. And all of that is going to be over 2 times 3.95, which is 7.90. So now let's take it another step. My x is equal to this value plus or minus the square root of 0.0025. So when I subtract a negative, they cancel out and I am adding 0.1264. So underneath the square root, I have a positive value of 0.1289, all divided by 7.90. So I'm going to do the adding first. So I'm going to take a negative 0.05 and I'm going to, well, I guess I should do the square root. So the square root of 0.1289 do it this way. I get 0.3590 all over 7.9. So now we can solve for our x. So we're going to have two x values. So I'm first going to take a negative 0.05 and I'm going to add 0.359 and then divide it by 7.9. So I get my first value of 0.0391. And for my second value, I'm going to take my negative 0.05 and I'm going to subtract a 0.359 and then divide that by 7.90. And I get a negative 0.05, I'd call that 18. So which value do we use and how do we know? Well, you have to remember what that x represents. That x represents a change here. Now, if you had put the wrong sign in your change column and you had maybe minus 2x in your products and plus 2x or plus x's in your reactant sign, then both of your x values would end up negative. And that's how you would know that you did something wrong at the beginning. But how do I know which one of these to use now? Well, because we can't, if we multiply this negative value by 2, it's still a negative value, and I can't have a negative concentration. So I know it's not going to be the negative value. So I know my x is going to be this value here. So at equilibrium, the concentration, the pressure, not concentration. The pressure of the N2 is going to be equal to 0.8 minus 0.0391. So I would get a pressure of 0.961 atmospheres at equilibrium for N2. So for O2, it's going to be 0.20 minus the x value, same x value, and I get a pressure of 0.161 atmospheres. So the pressure of NO at equilibrium, specifically asked for NO in the question, I ignored that, is 2 times my x value, 0.0391. And so the pressure of NO is 0.0782 atmospheres at equilibrium. So that is the value that answers the question. For the next question, we have a mix of easier and not so easier, but we do have an extra layer. Now you are expected to carry forward the information that you have gained from Chemistry 1. So we would take this 1 gram of water and 2 grams of Cl2O or dichloroxide. All of a sudden I couldn't name that. And you are expected to be able to pull a concentration out of that. You have gram values, you have a volume. So remember, 99% of the time in my class when you see grams, you do need to convert that into moles. So I'm going to start with my grams of water. And there are 18.0 grams of water in 1 mole. So I need to convert that into moles, 1 divided by 18. And I get 0.055, I'll stop there, 6. And I know that's too many significant digits. I'm trying to avoid some rounding error. So you do that that's moles of water. It's in a 1 liter flask, so that's also the molarity. And for my next one, 2.0, need to find the molar mass. Remember, to find the molar mass, you go to the periodic table and you look up the mass of each of your elements. Multiply them by the subscript, that's your stoichiometric coefficient for the compound, and add them all together. And I get a molar mass of this one, 86.9 grams for my dichloromonoxide. So I take 2, divide it by 86.9, and I get 0.0230, and that is moles of dichloromonoxide. Now we need to calculate the concentrations of all species at equilibrium. So first, let's see, I have H2O, Cl2O, 2HOCl. Initially, I have a concentration of 0.0556. Initially here, I have a concentration of 0.0230 and no product initially. So I will change and I will take away from my reactants and I will add to my products. So at equilibrium, I have a concentration of 0.0556 minus X for H2O, 0.0230 minus X for Cl2O, and 2X for HOCl. So now we have to fit everything into the K expression. So the K expression here is going to be the concentration of my product, HOCl squared, because the balanced chemical equation has a 2 for the coefficient of my product, all divided by H2O, the concentration of H2O, times the concentrations of Cl2O. Now, usually we don't put water in the equilibrium expression, but because water is a gas here, it goes. If water was a liquid, it wouldn't have a concentration, so it wouldn't be part of the equation. So now I need to fit these values into my K expression, and my K expression has a value of 0.090. So I'm going to fit that in there. My 2X, which is going to get squared, that's the concentration of my product, and then I put my reactant values in. And I'm going to run off the page. So now we're going to get a little bit messy and tricky. Let me call up another page. And we will use this. So I'm going to multiply both sides by my denominator so that I end up with 0.090 is equal to, well, times my denominator, and I'm going to leave it in this form. And that will be equal to, and I'm going to square this. So 2x all squared is 4x squared. So now I'm going to expand my quadratic, and I'm going to use, again, the FOIL method. So I'm going to leave this 0.090 part out here, and I'm going to multiply 0.0556 times 0.0233 for the first. And so the first, I get a 0.0012. Oh, that's a 95. Then the outsides, so my 0.0556 times a negative x, so I'm going to subtract a 0.0556x. My insides, so negative x times 0.0230 is a negative 0.0230x. And then finally the last, so negative x times negative x is a positive x squared. And all of that is equal to 4x squared. So now I need to distribute this 0.90 part. So when I distribute this 0.90, or 0.09, I should say, 0.00, and I multiply 0.09 times 0.001295, I get a value of 0.123116. I'll call that 6. So when I distribute this, I'm going to start writing this in scientific notation. I think that's going to end up easier. So this is 2.07 times 10 to the negative 3 plus 0.090x squared, and all of that is equal to 4x squared. So I'm going to combine my like terms here. So 5 times 10 to the negative 3 and 2.07 times 10 to the negative 3. Both of those are negative, so I'm going to have, let's call this 1.17, 2, 3, 4. Okay. Now I need to get all of these terms on one side so that my entire quadratic equals 0. That way I can use the quadratic formula. So I'm going to subtract both sides. I'm going to subtract 0.090x squared from both sides and get 3.91x squared. Then I'm going to add this 0.707 times 10 to the negative third to both sides. Then I'm going to subtract 1.17 times 10 to the negative fourth from both sides so that all of this equals 0. This is my A term, this is my B term, and this is my C term. So to do it the long way, x is going to be equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And you can do it the long way, or you can put everything into the quadratic equation solver. So as before, we're going to use a's 3.91. So you use the same. It's the same idea. All you have to do is put it in. Just make sure that you have the correct sign. So my b value is a positive. See, that would be 0.00707. And then my c value is a negative 117. So then we have our roots, we have our values. So x is either a negative 0.00644 or a positive 0.0046. So going back to my original equation here, it can't be negative because we just can't have a negative concentration. So x is going to be equal to the positive value given here, 0.00464. Capital M for molarity. So what are the concentrations of this species at equilibrium? Well, I'm going to take the concentration of my water, so 0.0556 minus the x value, 0.00464, so I will have a concentration of 0.05, I get 0.96, I'd round that to 10. And let's see, I have 2 significant digits, so I would probably just round it right there. And the concentration of my dichloromonoxide is going to be equal to 0.023 minus 0.00464. So I get a concentration of 0.018 capital M molar. And the concentration of HOCl is going to be 2 times my x value, 0.00464. So I get a value of 0.009, I get a 28, so I'd round that to 3. So those are the values for that one. This one goes a little bit faster and is a little bit easier. So I'm starting with the same equation. I have water, dichloromonoxide, and that forms this product. Initially, I have none of my reactant, and I have 1 mole of product in a 2-liter flask. So 1 mole in a 2-liter is a 0.50 capital M molarity, and that's what we're working in here is molarity. So I'm going to change. I'm going to add x's to my reactant side, and I'm going to subtract x's from my product side, so that at equilibrium, I have these values. So I fit all of that into the K expression, and the K value is still the same, 0.090. And that is going to be the product squared, 0.50 minus 2x squared, over x times x. Now, this is one of those cases where you don't have to make it any harder for yourself than it already is. We can simply take the square root of both sides. And when we take the square root of both sides, I can't work my calculator fast enough, I get 0.30 for the left side, and on the right side, I have 0.50 minus 2x over x. I multiply both sides by x, Then I'm going to collect my x terms. So I'm going to add 2x to both sides. So I get 2.30x on the left is equal to 0.5. Now I'm going to divide both sides by 2.3, and I get an x value is equal to 0. I'm going to check my sig figs, 2 sig figs, 0.22 capital M molar. So the concentration of H2O is equal to the concentration of Cl2O, which is 0.22 capital M molar. In this case, the X value is the equilibrium concentration. The concentration of HOCl is going to be equal to 0.5 minus 2 times the X value. So I'm going to have a concentration of 0.060 for 2 sig figs, capital M molar. So you see this equilibrium lies pretty far to the left or pretty far towards the reactant side because there are many more reactants than there are products. Now with this problem, we're going to start with a vessel that's filled with 12 atmospheres of CO. So I'll put my 12 here. 12 atmospheres of water. This is initial. And the reaction progresses until equilibrium is established. So I have none of my products. Determine the pressure of each species. So we're going to change by removing reactants and adding products. Now this is a 1 to 1 to 1 to 1. Just double check whenever you're given a chemical equation that it is balanced. And then at equilibrium, then we have 12 minus x, 12 minus x, we have x, and we have x. So the K expression is going to be, or this is a Kp that we're dealing with here, the pressure of CO2 times the pressure of H2 over the pressure of CO times the pressure of H2O. All of that is going to be equal to 4.24. So I fit in all of this equilibrium stuff that I have. And for my products, I have 2 x's, so that's going to be x squared over 12 minus x, and that's going to be squared because 12 minus x times 12 minus x is 12 minus x squared. Now this is another case where you don't need to make it any harder than it already is. And we can take the square root of both sides. So when I do that, I get a value of 2.06 on the left with x over 12 minus x on the right. So I multiply both sides by 12 minus x, and I get 24.7 minus 2.06x is equal to x. I'm going to collect my x terms by adding 2.06 to both sides. Now, to get x alone, I divide both sides by 3.06, and I get an x value of 8.08, and this time it is atmospheres because we are dealing with a Kp. So this 8.808 atmospheres being x, that means the pressure of CO2 is equal to the pressure of H2, which is 8.08 atmospheres. For CO, let's see, the pressure of CO is going to be equal to the pressure of H2O, which is 12 minus this 8.08, which is 3.92. I'm looking for sig figs. We need 3 sig figs. So we'll go with that, even though it's not quite. Okay, to do the Sig Fig analysis, so I started with 12.0 and now I'm subtracting 8.08. So really, I should end here at the tens place. That would be the right way to do it. So the pressure of CO and the pressure of H2O would be 3.9 atmospheres. And for this problem, we have one we have to work all the way out. So we have this reaction, and we're found that the mixture contains 0.0200 of, let's see, this is our reactant. So this is going to be our initial 0.0200 M. And our product, we have 0.0300 M. We need to determine the concentrations at equilibrium. So we need to know which way this is going to shift first. So I need to calculate my Q value. My Q value is analogous to my K value. So I'm going to take the concentration of the NO2, the product, and square it because there's a 2 for the coefficient there. And then I will divide that by the concentration of my reactant. And I'm not squaring that because there's only a coefficient of 1 in front of that. So I'm going to insert the values that I was given for the concentrations. And so for the product, then I have 0.0300, and I'm going to square that, divided by 0.0200. So I have a Q value is equal to 0.045. Now this Q value, see the Kc value here, this 0.464 times 10 to the negative 3, 0.00464. Now you can compare these numbers. You see the Q value is greater than the K value. So we need to decrease our products in order to make this smaller. So I will take away my change. I will take away 2x from the product side. I'm going to take away a 2x because there's a 2 here. Otherwise, it would just be x. And I will add some amount x to the reactant side. So at equilibrium, the concentrations will be 0.0200 plus x on the reactant side and 0.0300 minus 2x on the product side. So now I can fit this into the K equation using the value that I was given for K. So my 4.64 times 10 to the negative third, and this is just another way to represent that. It's nothing special. And that's going to be equal to the value of my product at equilibrium divided by the value of my reactant at equilibrium. So this is one of those times where you can't simplify anything and it's just not going to work out all nice and pretty, like by taking the square roots of both sides. That's not going to work here. So we do need to multiply both sides by the denominator. So I will write it out the long way. And now I'm going to distribute this 4.64 and I get 9.28 times 10 to the negative fifth plus 4.64 times 10 to the negative third x is going to be equal to this 0.0300 plus 2x squared. Now I'm just going to work that over here real quick for those of you who need a brief primer. So when we square something like this, what we're doing is we're taking this and multiplying it by itself. We use the same FOIL method. So the outsides, 0.0009, and then, or I'm sorry, the first, not the outsides, then the outsides. But since the outsides are the same, I'm multiplying this 0.03 times 2x. I'm multiplying 2x by 0.03. I can just take 1 and then multiply that by 2. So I get a minus. All of a sudden, I feel like maybe I have the wrong, that's a minus. There we go. Minus 0.12x, and then the last. So negative 2x times negative 2x is a positive 4x squared. So now I'm going to move that business over here. Now I'm going to gather my like terms. So because I like a positive a value, so I'm going to leave this like this. I'm going to subtract 4.64 times 10 to the negative third x from both sides. And I don't get anything that's, well, I do get something that's relevant. I misspoke. So I subtract that from both sides. I get a value that doesn't make any sense. .11536. Nope, I did that wrong. So that's a negative 0.12. So I'm going to add that together and I get a negative. Don't confuse your negatives. I feel like I'm confusing you. 6.4, that's an x. Now I take this 928 times 10 to the negative fifth away. So I subtract that. and I get 8.072 10 to the negative fourth, and that all equals 0. So as before, this is my A value, this is my B value, and it is negative, and this is my C value, and it is negative as well. So I'm going to take this over to the quadratic equation solver. My A is 4, my B was a negative 0.12464, and my C was a negative 308072. So my X values given, I have a positive and a negative root. I have an X is 0.03666 and a negative 0.00550. Go back to my problem. And we could actually, negative 0.03. Well, this time, the answer is not going to be, and I made a mistake, and I'm going to tell you how I found that mistake. So see if I can get back there. So I had these roots, and my positive root is 0.0366, and my negative root is 0.0055. Now, I went back to the problem, and I was going to insert my root. Now, my positive root is 0.0366. Well, if I put that here, multiply it by 2, I've gotten rid of all of my product. Or more than all of my product. So that can't occur. So I went back through everything, and this Q value checks out. We do need to shift this way. That is correct. The problem was when I subtracted this from both sides, and what happened is I made this negative and it should be positive. So I wanted to show you that that was a mistake that I made. It is common to make these mistakes, and I get it. Show me your work so that I can find where you have made your mistakes and give you most of the credit. So now I have two roots. X is 0.0219. I'm going to call that 220. And X is 0.00918. Go back to the problem and let's see which one fits. So if I write those roots, I'm going to use a different color. So I have X equals 0.0220 and X is 0.00918. Now here I have 0.03 is what I'm starting with. If I multiply this by 2, so 2x1, 0.022 times 2, then I have a value of 0.044. And that value is greater than this value, so it cannot be x1. So this must be the correct root for this problem. So the concentration of my reactant N2O4 at equilibrium is going to be equal to 0.0200 plus X, which in this case is 0.00918. And I get a value of 0.029. I get 18. Let's check sig figs here. I have 3 sig figs there, so I would call this 0.0292 molar. And the concentration of my product would then be 0.0300 minus 2 times my X value. So 2 times 0.00918. And I get a value at equilibrium of 0.0116 capital M molar. So if your roots do not make sense and you're in a quiz and you're under a time crunch, write down that you know something doesn't make sense, and I will find your mistake, and as long as you've done most of the chemistry correctly, you will get most of the credit.